Okay, everybody, now let us complete our discussion about the concepts of the wave motion. Here, one of the most important concepts here, it's the amplitude. What is the meaning of the amplitude? Of course, you know that the pendulum, for example, was standing at the original position in the middle, and it moved to the two sides, right and left. Here this pendulum moved to the left or to the right by the same distance. The distance to the left is the same the distance to the right. Here this distance equal the same value of this distance but opposite in direction. This means this maximum distance away from the rest position. This maximum far away from the rest position is called the amplitude. Why we call it the maximum distance? Because this is the distance between the original position and the maximum point away from the rest position. This maximum point is called amplitude, of course. What about any point here in between the original position and the maximum point? Any point here between the maximum point and the original location, we call it only displacement, because it's a distance but it has a certain direction, so this is called a displacement. So the distance between any point between the maximum point and the original is called the displacement, but the distance between the maximum point and the original location, we will call it amplitude. So the amplitude, it's the maximum displacement of the vibrating body away from its rest position. If we call the rest position A and the maximum point to the left it's B and the maximum point to the right it's C, so the AB will equal to AC, and it will be called amplitude. But the displacement, as we discussed together from a while, displacement, it's the distance of the vibrating body away from its rest position at any instant, but it isn't, of course, the maximum point B and C. And as we discussed before too, here the amplitude represent quarter of complete oscillation. Why it's a quarter of your complete oscillation? Due to, we said, the pendulum start moving from rest to B, then return to A again, and moved from A to C, and return from C to A. How many amplitude we made during the journey? Try to count with me. From A to B, this is 1. From B to A, this is 2. From A to C, this is 3. From C to A, this is 4. So we have here 4 amplitudes. So the complete oscillation contains 4 amplitude. What about the 1 amplitude? The 1 amplitude represents 1/4 of the 1 complete oscillation. So we can say that the amplitude equal quarter of complete oscillation. What about its time? The time of complete oscillation equal 4 times the time of amplitude. So the amplitude, its time, equal 1/4 the time of complete oscillation. And this amplitude, of course, is a distance, or it's a displacement. So its length, we can measure it by the measuring unit of the length, which is the meter. The meter is the measuring unit of the amplitude. The next concept is the frequency. What is the meaning of frequency? Frequency, its symbol is like that. It's nu. This Greek letter is called nu. Nu equal, try to think with me, frequency. What is the meaning of frequency? Frequency means we make the same process continuously related to time. So the frequency, how many you made this process related to time. If you are trying to move by your upper part from forward to backward during your sitting on the chair, the number of moving forward and backward related to time, this is called frequency. So nu equal n over t. N is the number of complete oscillations over t, the time of the oscillation. So nu equal n over t, and it can be defined as it's the number of complete oscillation made by a vibrating body in 1 second. So from the rule we can find its measuring unit. It's measured by n, measured by the cycle or oscillation, and the time measured by second, of course. So the measuring unit will be oscillation per second. It's oscillation per second. Oscillation per second equal or the same hertz. Hertz is the name of one of the most famous scientists in our field, physics here. Okay, what about the relation between frequency and the time? We will study this relation after a few seconds, but before that we will discuss what is the meaning of periodic time. Here, don't get mixed between periodic time and period. Periodic time, of course, it's a time. Periodic time, it's a time. But period means one wave. Period means one oscillation. Period means complete oscillatory motion. But periodic time, it's the time of making one complete oscillation. So it's the time taken by a vibrating body to make one complete oscillation. So T here, if I told you that the vibrating body made 100 turn in 10 seconds, what is the time of one oscillation? Again, a vibrating body made 100 cycles in 10 seconds. What's the time of one cycle? The time of one cycle will be calculated by the rule total time over total number of turns. Total time over total number of turns. So it will be 10 seconds divided 100 turns. So it will be 0.1 second. This is the periodic time. So T equal total time over number of complete oscillation. T, what is the relation between T capital and the time of amplitude? T capital is the time of one complete oscillation. And the complete oscillation consists of 4 amplitudes. So T equal 4 T of amplitude. Due to the amplitude is quarter of the complete oscillation and its time. So its measuring unit will be, of course, second. Of course, you know that. Now let us discuss together the relation between frequency and the periodic time. frequency and periodic time. The frequency, its symbol is nu, as you see here, and the periodic time, its symbol is T capital. Don't get mixed between T capital and T small. T capital is the periodic time, and T small is the total time of the motion. You studied that nu equal n over t. N is the number of waves, and t is the total time of making wave. T capital, it's t over n. T is the total time. N is the number of complete oscillation. So here the relation between nu and t, as you see here, t is the reciprocal of the nu, and the nu is the reciprocal of t. Then we can define the frequency. It's the reciprocal of the periodic time. So nu equal 1 over t capital. This is the relation between frequency and the periodic time. As you see here, nu equal 1 over t capital. This is the relation. So frequency equal reciprocal of periodic time. From here, the relation, of course, between frequency and the periodic time, as frequency increase, the periodic time will decrease. So it's inversely proportional. We have here the two relations here, this relation and this relation. Of course, you know that both are inversely proportional, but what is the difference between this part and this part? I think you know the difference between both. This is a straight line, so it's inversely proportional due to the relation between nu and 1 over t. Here, this is a curve between nu and t, so it's inversely proportional too, but the difference between this and that, this is called inversely proportional, but by a non-uniform way. The non-uniform, but here this is a uniform way. Okay, now you know the relation between frequency and the periodic time t. Here, a problem, finally, we reach it to a problem to understand the relation between the physical quantities in this part. This part is very important. Here, the problem, tuning fork makes 500 complete oscillation in 10 seconds. So here you have n, the number of complete oscillation, it's 500, and the total time, it's 10 seconds. Calculate the frequency and the periodic time. Frequency equal n over t. N here 500 and t is 10. So frequency will be 50 cycle per second or 50 hertz. The periodic time t capital, it's 10 over 500 due to t capital, the periodic time, it's the total time over number of waves, it's 10 over 500, so this will be 1 over 50. 1 over 50, this means 0.002 second. 1 over 50, it's 0.02 second. Here, before leaving this part, I want to let you know about two notes. Note number 1, the motion of the pendulum can be represented by the figure in front of you. This figure in front of you, this is called sine curve. As you see here, this sine curve move to reach to the maximum peak, then return back to the original location and move to the peak to the other side, then return to the original position. As you see here, this peak is to the opposite direction, to the positive direction, and here this peak to the negative direction. Both two peaks are the same value but opposite in direction, this is positive and this is negative, we say that this figure has something of harmony. So the simple oscillatory motion like pendulum is called simple harmonic motion. This is simple harmonic motion. Number 2, this simple harmonic motion can be represented by a lateral sine curve, as you see in front of you here. Number 3, the mechanical waves need a material to travel through. Without the material, the sound wave, for example, can't propagate, can't move. Okay, let us discuss this part together. The sound wave can propagate through the media. This means sound wave can propagate through air and can propagate through liquids and also can propagate through solids. But let me ask you about the speed of propagation of this wave. The speed of propagation of this wave. What do you think? The speed of sound in air, faster or lower than liquid and faster or lower than the solid? What do you think? Try to tap by your finger on your disk and hear the sound in air, and try to put your ear on the surface or on your disk. Try to listen to the sound. What do you think? Which is stronger? Which has more strength? Try to think. The sound move through the water molecule faster or slower than the air? If you want to find the suitable answer, you need to understand the properties of each media of these carefully. Air has intermolecular spaces between its medium. This intermolecular spaces is very far, so the attraction force between its molecules is very weak. So the spreading of air from molecule to molecule due to the molecules carry the energy. So the energy jump from molecule to molecule. And here in air, the molecules are very far away from each other. So the jumping of energy from molecule to molecule take time. So the speed of sound in air is slower than liquid due to the intermolecular spaces between the liquid molecules smaller than the air. So the jumping is easier than the air. So the speed will get higher. And by the same way, the solid, the intermolecular spaces between the molecules of the solid is very tiny. So the motion or the spreading of energy of sound through the molecule of the solid, it will be piece of cake. It will be very easy. So the spreading of sound will have a huge velocity. So the velocity will increase. So the relation between the velocity of the spreading of the wave and the intermolecular spaces between the molecules of the medium, it's inversely proportional. As the distance between the molecules of the medium decrease, the spreading speed of the wave will be higher. So sound travels through solid faster than gases due to the particles are closer to each other. Okay. But we can't hear the voices of cosmic explosions that occur in space. There are a very tremendous explosions occur on the surface of the sun, which produce to us the sunlight. But we can see the light and we can't hear the explosions, the cosmic explosions. We can't see it. Why we can't see it? Why we can't hear it, sorry, but we can see the light produced from these explosions. Dear student, of course you know after you're studying for this chapter of waves that the light is electromagnetic waves, so it can propagate through vacuum between the Earth planet and our star sun. But the sound is a mechanical wave. It needs a medium to propagate through, need molecules to jump on it, need carrier of the energy to carry. So sound can't move, can't propagate through the space. So we can't hear the voices of cosmic explosions that occur in the space. And by the same way, the astronauts on the surface of the moon, for example, there is no air on the surface of the moon. So the astronauts used wireless devices to communicate in space. Why? Due to these devices convert the human being voice to electromagnetic waves, and the electromagnetic waves can travel through the space. So one person has a sender and another person has a receiver, and the electromagnetic waves produced from the sender and reach to the receiver. So the astronauts need to use the wireless devices to communicate in space. But here I want from you to take care of a very important point. The rules of physics that we found, that we depend on, which we study here on the surface of the earth, we can't use it at the space. There is a great difference between the space and the surface of the earth. So the rules which control the relation between physical quantities in the space is completely different than the rules which control the relation between physical quantities here on the earth. Now let us move to discuss together a very important, very critical part, which is the difference between transverse wave and the longitudinal wave. Before starting to differentiate between both transverse wave and longitudinal wave, I want from you to know that the only factor which classify the waves to transverse or longitudinal is the theta, the angle theta. The angle theta between two directions. These two directions is the direction of wave propagation and the direction of molecule motion. Again, the only factor which differentiate between the transverse wave and the longitudinal wave is the angle theta between two directions. The direction of wave propagation and the direction of motion of the molecule of the medium. So take care of this theta and learn how you can calculate this value. Now let us start our talking about first transverse waves. Transverse waves It's the wave in which the vibration of the medium of particles is perpendicular to the direction of the wave's propagation, as you see here. But we need to understand this part to make you able to deal with the questions of the smart application on this part. If you are sitting here, imagine this shape is the waves of the water, and you are sitting here in a boat. What do you feel during passing the waves from under the bottom of the boat? You will feel, of course, that the boat moves ups and downs, and doesn't move forward or backward, but it's only move upward and downward. But the wave pass from under the bottom of the boat in one direction, as you see here. So here, this is the direction of wave propagation. This is the direction of wave propagation. But the molecules of the water which carry the boat move ups and downs. So here, this direction is the direction of the molecules of the medium, and this direction is the direction of the wave propagation. The angle here between the two directions equal 90 degrees. So any wave make angle 90 between the direction of wave propagation and the direction of molecules of the medium equal 90 degree, you will call this wave by transverse wave. This wave, as you see here, make a maximum displacement, a high peak in the opposite direction, and make a amplitude here, another amplitude, a maximum displacement, but in the opposite direction. Here, this displacement in the positive equals the displacement in the negative. So this part is called the crest, and this part here is called the trough. The crest, it's the maximum displacement, but in the positive direction. In here, the trough, it's the position where the molecules make maximum displacement, but in the negative direction. And we can put another definition for crest and trough. Crest is the point where the potential difference of the molecules is very high. It's very high here, and its kinetic energy is very low. Here, the trough, by the same way, it's reached to the peak, but in the opposite direction, which is called the negative direction. This is the difference between crest and the trough. So this is the first crest, this is the second crest. Here, this is the first trough, and this is the second trough. We want to know how we can calculate the wavelength here for this object. The wavelength, it's the distance between 2 points. These 2 points have the same phase. You now can tell me what is the meaning of same phase. Same phase means the 2 points are located at the same position and the same direction. What about, for example, this point and this point? Is these 2 points have the same phase? Look, this point and this point are located on the original position, so they have the same location. But the direction of motion in here is upward. The values increase. But here, the values decrease. So the motion, it's up, here the motion to down. So the direction of motion is different. So these 2 points can't have the same phase. What about this point and this point? This point here and this point there. This is called, this part here is called quarter wave. This is quarter wave. This part is quarter. This is the first quarter, and here this is the second quarter. So this is called quarter. Quarter means half complete revolution. And of course, you know from math that the complete revolution equal 36 degree. 360 degree. 360 degree. So quarter of the wave, complete wave, 360 divide 4, this will be 90 degree. So the difference in phase between this point and that here, it's 90 degree. So this point and this point have different phase. This point and this point have different phase. What about this point and this point here? This and that. This point and that are located on the rest location. It's the original position. So both have the same location. This is moving upward, and here this is moving upward too. The values here increase and the values there increase. So the direction is the same. From that, the direction the same and the location the same. So A here, if this is A and this is B, A and B, these 2 points have the same phase. And the difference between 2 points have the same phase, this distance, we call it wavelength. So this is one wave. From here to there, this is one wave. So count with me, this is one wave, and here, this is the second wave. So the number of waves in front of you here, it's 2 waves. So the definition of the wavelengths, we can say that it's the distance between 2 points along the direction of the motion, but these 2 points have the same phase, which means have the same location and direction. But there is no sign in this definition for the transverse wave, due to the transverse wave consists of crests and troughs. This definition is called general form of the wavelength. General form. The distance between any 2 points have the same phase. This can be existed in transverse wave and can be existed here in the longitudinal wave. But we need another definition which concentrate on transverse wave. Here, this point and that, these are called crests. These 2 points are located at the same location here. Try to figure out the direction. Here the values decrease after that and the values decrease after that. This means the direction of these 2 points will be the same. So the distance between these 2 points will be called wavelengths. Why? Due to these 2 points have the same phase. Why have the same phase? Due to they have the same location and the same direction of motion. By the same way, the troughs, the distance between these 2 troughs, they are located at the same location, and here the direction of motion in this direction and the direction of motion in here in this direction. So same location and same direction. This means the distance between these 2 points will be called wavelengths, as you see here. And the examples of the transverse wave, as you see here, it will be water wave on the surface of the water. Don't forget that. And we can use a string or a rope to make a transverse wave by putting the end of the rope, one end of the rope inside your hand, catch it by your hand, and the another end fix it on the wall, and try to move your hand ups and downs. You will find that the rope make waves like that, ups and downs, and this will be crests and troughs, which is called transverse wave. Now we are ready to move to discuss longitudinal wave, but before moving I want to repeat this for you. The factor which help you to know the transverse wave, it's the theta between the direction of wave propagation and the direction of molecules of the medium. If this direction equal 90 degree, then you can say that this wave is called transverse wave. What about the longitudinal wave? Longitudinal wave, we will study only here sound in air. Sound in air, try to imagine that these are the molecules of air, and I have here a tuning fork. After hitting the two branches of the tuning fork on the edge of a table, the branch of the tuning fork will move to left and right by this way, to left and right. This branch will make a pressure on the molecules of the air. Then some pressures will be close to each other, and some molecules will be away from each other, and another area here the molecules are close to each other, and the area here the molecules away from each other. So these areas where the molecules are close to each other, we will call it compression, and the areas where the molecules away from each other, we will call it rarefaction. So longitudinal wave consists of compressions and rarefaction. And as you see here, this is the direction of motion of the sound, here in this direction. And as you see here, the molecules of air which carry the sound energy move by this way, to right and left, to right and left, to right and left. So this is the direction of sound, and by this way, this is the direction of molecules of the air. So the direction of the air molecules and the direction of the sound, these two directions are parallel to each other, so theta between them equals 0. From here we can define the longitudinal wave. It's the wave in which the vibration of the medium particles is along the direction of the wave propagation, making angle 0. And it consists of compressions and rarefactions. Here we can classify the we can define the compression by its area where the molecules of the air get close to each other. As the molecules get close to each other, this means the density will increase in these parts, and of course as the density increase, the pressure will increase too in these parts. But here in these parts, the rarefaction, it's the area in which the medium particles are far from each other. It's far from each other, so the density will decrease, and as the density decrease, then the pressure will decrease too. Here we want to define what is the meaning of the wavelength of this part. The wavelength, by the same way, it's the distance between 2 points. These 2 points have the same phase. Again, same phase means these 2 points have the same location and the same direction of motion. Try to look at the figure in front of you and tell me where the points which have the same phase. The points which have the same location. We will deal with the center of the area. We can't deal with the edge of the areas. But what about this point and this point here? These 2 points, these 2 points have the same phase? Of course not, because this is air, this is compression, and this is rarefaction. So the distance here, it isn't called wavelengths. Okay, what about the center of the compression and the center of the second compression? Here, this point, the center of this compression and the center of this compression, both have the same phase, due to they have the same location and the same direction. And by the same way, the center of this rarefaction and the center of the second rarefaction. So we can define the wavelength of longitudinal wave. It's the distance between the center of 2 successive compressions or rarefaction. This is the wavelength of the longitudinal wave. Don't get mixed between transverse wave and longitudinal waves. The theta is the only factor which let you know what's the difference between transverse and longitudinal. If theta equal 90 degree, this will be transverse wave. If theta equal 0 degree, here the wave will be called longitudinal wave. So take care of that. Here, don't forget, we studied sound wave in gas, we studied sound wave in air, and we studied the water wave on the surface of the water. Now you can answer any question about transverse wave and longitudinal wave, and you can determine the type of wave as you wish by figuring out the direction of wave propagation and the direction of molecule motion. Now, before moving to some important points, I wanted to ask you some questions to practice about determining the type of motion, which may let you be more smart in dealing with type of questions. Let us move to try to practice this part together.